So welcome to the last session of the day and I guess the week. Oh, no, are there sessions tomorrow? Okay, so this is Julie Loisel. She's from University of Texas AM, and I'm Angela Gallego-Sala from University of Exeter, and we're going to talk to you about getting to know your peatlands, the largest natural land carbon stores on Earth. Julie.
Yes, thank you, Angela. Well, who are we? First of all, we have the opportunity to be representing a large group of scientists from the group C-PEAT. C-PEAT stands for Carbon in Peat on Earth Through Time. And what we do is we look at the past, essentially, to help document what is happening to peatlands today and in the future. So we are interested at peatlands yesterday, 10 years ago, 10,000 years ago, and even hundreds of million years ago. And essentially, we have over 250 scientists currently that are part of this group. And Angela and I are the co-leads of this community. And really, we feel like a family. And what we do is we utilize what we will refer as the Paleo Approach, which means essentially just looking at the past dynamics to inform, again, the future. And for this meeting today, what we did is we asked a few of our colleagues to send some sites and pictures and videos and also site descriptions from some of the sites that they are analyzing now or that they analyzed in the past. And this is an interactive map that you can look up online to the websites that are indicated here. Currently, there's about 80 sites and they're from 20 different countries. If you have sites that you would like to add to this map, you're welcome to do that. Those are going to be forever displays. And the Paleo Approach here, what is it? Well, essentially, we go around the world. We have sites, as you could see, from all over the place. And we bring coring devices, and we sample the stratigraphy of peat cores. This is what it looks like when we are in the field. And then we use very fancy equipment, such as kitchen knives, to cut the slices of peat and essentially tell the history of the peat from the bottom layers all the way up to the present. And we look at the relics that are left in the peat layers. And here you see a few examples, including testate amoeba on the right-hand side. Those are microorganisms that tell us something about water table depth changes through time. And then in the center, we have examples of pollen grains and spores that are telling us how the vegetation has changed around the sites through time. And we can connect this to changes in temperature and precipitation. And of course, looking at the peat layers themselves, which are made out of peat remnants or plant fossils, we can recognize the kinds of plant that existed. And so we can really analyze the connection between past changes in climate and the way that the peatland developed through time. And today, we have the opportunity to display some artistic renditions of peat landscapes, and they are around us in the room for those of us present, so you can look at them. But we also have high-resolution PDFs for anyone who wants to use them. And the artist who drew those, and there's also those relics that are drawn as well, is Patrick Campbell, and it's really beautiful work.
And we will put it in the online Peatland Pavilion.
Absolutely, yes, yeah. And so today we will talk about a few ways that our community, and again, we're representing large synthesis of work that hundreds of people have been doing over the past 10 years or so, how we utilize this paleo information to try and connect with people that have been here, either talking about restoration or the future carbon balance of peatlands. So 4 short case studies. The first is, okay, we all know that peatlands contain a whole lot of carbon, but how do we know this number? Well, it's part of the research that we are doing in our group, so we'll talk about this a little bit. And then how is climate affecting peatlands and that capacity to absorb carbon through time? And then we will talk about peatland extent as well, if we expect peatlands to grow or to shrink and where in the world, and then some future direction for our work. Okay, so I get to start. How do we quantify the peatland carbon stock? Well, peatlands, as you know, are all over the place. There's some examples here from the tropics, from the high latitudes, the northern in green, the southern in red. Here you see a peatland with trees, some peatlands with no trees. This one here is an Antarctic moss bank. And so on every continent we have peat, and they accumulate large amounts of carbon through time. This is one of the maps that has been done, but there's many more now that are arguably better. And we have known for, I would say, 30 years, some amount, the knowledge that there's a lot of carbon in those sites. from Gorham, in 1991 already. But now these estimates are changing a little bit through time because now, first of all, we have a better knowledge of tropical peats, although this is not good enough yet. And we have even some studies that suggest even larger carbon sinks. But we won't get into any of those details today, but just to give you a sense of the size of those carbon stores. And although it's been a long time that we've known about the carbon store, it has only been recognized by the IPCC in the AR5 report, so the previous report, as an important carbon sink to the biogeochemical cycle of Earth. And you can see exactly, thank you, that peat accumulation over the past 10,000 years has had a net cooling effect on the global climate. Greater than, for example, the CO2 fertilization effect that many of us are aware of or familiar with. And here I want to show you an example of how we can utilize a lot of the paleo information to inform not only how much carbon is in those peatlands, but when was the carbon accumulating through time. And here, this is a synthesis that we ran through C-PEAT back many, many years ago already. And this one was utilizing 268 cores. This is only the northern hemisphere, north of 45 degrees. And what we did is we look at all these peat cores and we use radiocarbon dating along the cores, and we can calculate how much carbon was stored in 500-year increments, which are those bins that you see at the bottom. And so from 12,000 years ago on the bottom right, all the way to today on the left, you see that overall there's, well, and first of all, the higher carbon accumulation rate happened between 8 and 10,000 years ago, which sounds interesting and perhaps strange, because you would think, well, this is so old, it's probably all decomposed and compacted at the bottom of the cores. But in fact, we think that the climate back then was favorable for peat accumulation, and I'll get back to this in a second. And then after that, you see that from 8,000 years ago all the way to maybe 1,000 years ago, the carbon accumulation rate has been slowing down, and that has to do to the fact with climate cooling during the Holocene. And then you have this recent uptick of carbon accumulation rate on hemispheric scale. And there's two things happening here. There's the fact that this peat is really recent, so it hasn't decomposed quite yet, and it hasn't reached this kind of more stable peat. But also the fact that the climate conditions today might be impacting in a positive way peat accumulation. In other words, maybe the warmer climate conditions in the northern hemisphere is accelerating peat accumulation. So that is one of the big hypotheses that we've been developing over the years. So here you see solar insolation in summertime in the northern hemisphere, and you see that it was really the warmest 10,000 years ago, and through time we see this decline in climate or in temperature, and that again we think is linked to the carbon sink capacity of the northern hemisphere peatlands. And then what we do, because this only tells us about vertical accumulation rate in peats, but we're very interested in knowing the lateral spread of peatlands across the landscape. So instead of looking at multiple cores vertically, we have thousands of cores across the landscape, and we look at the oldest sample at the bottom of each core, and we date that. And here, those bins are smaller, but they're showing you the initiation age of the peatlands. And so we use that as a way to, again, look at the peatlands spreading across the landscape. And same thing, you see that during the early Holocene, which was the warmest times, you have a lot of peat expansion because the landscape is, well, also just being deglaciated at this time. And so we have more space for peat to grow. And then when we combine vertical and horizontal, we can calculate the amount of net carbon sequestration by these ecosystems. And this is what you see here. And during the early Holocene, the net carbon balance of these ecosystems was over 80 gigatons of carbon per 1,000 years, which we estimate is more than enough to explain global decrease in atmospheric CO2 concentration that has been recorded in ice cores in Greenland. Now, just a quick update. Our synthesis is never over. We always welcome new samples and new cores. So now we have a new synthesis that is ongoing that has over 7,500 cores, and we're utilizing it to do some modelization of peatland lateral expansion and other. So my first short conclusion is that those past warm climates in the record indicate or suggest that warm conditions in the northern hemisphere might help peat develop laterally and also vertically, so store more carbon. But then the question is, will this happen in the future as well?
So I'm going to delve a little bit more into this idea of warming and how that affects the vertical accumulation of peat. So I'm going to ask you to think, I know it's very late in the day, but I'm going to ask you to think but it's a very simple equation. So how much peat is accumulated is the result of, apologies for the, for the acronym, is the result of photosynthesis, so how fast the plants are uptaking carbon from the atmosphere, minus the amount or the rate of decomposition, let's say simply put. So how much carbon is being basically brought into the system versus how much carbon, the bugs in the soil are decomposing and releasing back into the atmosphere. And the balance between those two things will give you how much peat is accumulating. And if you think about the response of this to warming, and I'm now asking you to think about where most peatlands are, so on the northern latitudes and high latitudes, then an increase in warming will actually increase photosynthesis because the plants at the moment are limited by the growing season length. And as you warm, they can actually photosynthesize for a longer period of time in the year. So your increase is this term. So with warming, this term increases. And if you think about the decomposition in the soil, all chemical and biological reactions increase exponentially with warming. So then this also increases. And this is then the overall effect cannot be foretold without knowing which of the two is fastest, because both are increasing with warming. So you don't know which one is going to win. And so you need to know whether photosynthesis will increase more or decomposition will increase more. And so this is why we don't have an easy answer, and we have to look at these past records. And so Julie showed you how you look at past records through time. And the other way we can look at these records is geographically. So we already have peatlands that are exposed to warmer versus colder climates. And so you can see here, this is just, so we took cores and we looked at the last millennium only, so a period of time, and we just look at whether they are accumulating a lot or less. And you can already see some spatial patterning, maybe darker colors, darker red colors lower down, and whiter colors on the northern part. And so darker red colors means more vertical accumulation, so faster accumulation. So again, what this is suggesting, and I'll show you in a more graphical form in a minute, but what this is suggesting is warming actually increases that vertical accumulation, which is what Julie was talking about with that thermal maximum during the Holocene. Warming actually increases vertical accumulation. And that sounds like good news to us, right? Warming is going to increase accumulation, and that means more drawing down of carbon from the atmosphere. Great. Okay, so we looked to see if this was true, so here on the y-axis is carbon accumulation again, and here on the x-axis is different environmental drivers. And you have here, this is the same representation, green is fence and blue is box, never mind. But you have the same representation. So this is photosynthetic or growing season radiation. So how much radiation gets to the site? This has a temperature effect in it because the longer, the warmer it is, the longer the growing season. So basically what you have is sites very high in the latitudes here. And as you come towards temperate, you're coming towards this part. And then as you come towards tropical, you're coming at this end of the graph. So basically colder, warmer, and more radiation as you come to this side. And this is the best predictor that we could find. To our surprise, moisture doesn't seem to be a very good driver of accumulation. So it functions a little bit like an on-off switch. If the system is wet enough, you will get accumulation, but then it doesn't explain, or we didn't use the right moisture index. That could be true. We tried loads, but we couldn't see a relationship with moisture. But we then used this growing season radiation relationship with accumulation, which you can see it's rough, like there is loads of things outliers, but we used it to then predict the future. Sorry, this is low latitudes are at this end, as I told you. Oh yes, I forgot. This is what we think we are seeing is that, you remember I said that photosynthesis increases with temperature? but increases in this shape. So it increases a lot at the beginning when you have only 3 days of growing season length. If you increase it a little bit, photosynthesis increases a lot. But when you get to temperate and towards tropical, you're not expecting photosynthesis to increase that much because the growing season is already the whole year. While respiration is increasing exponentially, like I said. And what we are seeing is basically the area under the curve is giving us that shaped bell curve that we see in the previous slide, in this slide. This bell-shaped curve is due to this relationship between photosynthesis, likely, I mean, this is just my conceptual understanding, but it may help you also understand what might be going on. And then you can use that relationship to try and, so we try and use that relationship to model, you know, it's a very rough model, but to model what might happen to that vertical carbon accumulation and to take that into the future. And I'm just taking one of the panels, you know, on the, let's say, worst case scenario, RCP 8.5, and a long way into the future, 2190. And what you can see is that it looks like the area's sort of tropical temperate peatlands may become a less of a sink, so red is less of a sink, while the northern peatlands may become more of a sink. So overall, peatlands do remain a net sink, but there is greater gains in the north and greater losses on tropical peatlands. This is really like, I want to say like a back of the envelope almost calculation, but you know, it's what the records are saying so far. But then loads of limitations to this. You know, we actually don't look at changes in peatland extent. These are likely to be very important in the future, and we'll talk a little bit about this. We don't take into account the CO2 fertilization effect that we know is important as well. You know, changes in hydrology, again, we don't take that into account. That is likely to change peatland extent, because if you don't have the right hydrology, you will not have a peatland there. And then we are not taking into account anthropogenic impacts. We are saying, you know, peatlands will continue to be a sink, but actually we know already that anthropogenic impacts have already tipped them over and they're a source already. So all of these things are the caveats of this sort of back of the envelope calculation. And then I just wanted to say, you know, in the good news of, you know, northern peatlands maybe becoming stronger sinks, there was a modeling study a couple of years back that suggested that northern peatlands, so the limit of growth of northern peatlands is actually quite large, and they have a big capacity to incorporate additional carbon. And, you know, this may be very important in the future. They said that this is only second only to oceans in the capacity of incorporating new carbon. The only thing is that, as we know, peatlands are a slow sink, so it may be in a long time frame. So the other question that we are interested in is knowing how peatland distribution might change, because very good, we think, you know, we know something about the vertical distribution, but what happens with the extent? And so there are now a couple of, okay, so I'm going to talk to you a little bit about how we think these 3 regions might change in the future. And I've actually taken this inspired by a talk by Gustav that is showing you where the peatlands are distributed in the world, because I'm going to talk about biome shift polewards. So if you imagine, this is where the biome is now. So the peatlands are you know, a lot of the peatlands are at this latitude, and then some are here in the tropics. And I'm going to talk to you how this may change in the future. So if you imagine the latitudinal spread, I'm going to talk to you a little bit about how those kind of distributions might change. But, well, I'm going to tell you about the projects that are ongoing. I'm not going to give you many answers. So in terms of Arctic, there is 2 community projects, let's say, you know, that involve a lot of the C-PEAT people community. One is increased carbon accumulation in Arctic peatlands, funded by NERC, and the other one is Tundra Peat, Northern Peatland Expansion, funded by NSF. And both look at whether this is, you know, what's going to happen to Arctic peatlands. You know, do we expect an ecosystem shift polewards I want to say northwards because most of the peatlands are north, but the peatlands south will go polewards, you know. And, you know, that combined with an increase in vertical accumulation, you know, will it mean that we will see actually more carbon accumulation in sort of the higher latitudes? These are, you know, ongoing questions. The projects are still ongoing and we don't have the answers yet. But I just wanted to show you, yeah, this is just what I said, but I wanted to show you that again, we use the Paleo approach for answering these kind of questions that are to do with the future of peatlands. So here, for example, what we do is in these types of landscapes, so very high Arctic, where the landscape is mainly bare ground and small patches of vegetation, we already see these kind of proto-peatlands appearing. And so we are basically measuring across here. So in these images, this is in Svalbard. And we basically measure, this is actually meters across the little patch of peat. And we basically measure, like Julie was saying, we measure the basal age and we see whether there is expansion outwards. So can we see expansion of peatlands in the Arctic already? Because this hypothesis of that we have that they are going to expand northwards is true or not. We also use other methods, but I just wanted to illustrate the paleo methods. That is what we are really. In terms of temperate peatlands, there hasn't been a lot of work on shifts of that, but you know, if you think about it, they're at the southern edge of the northern distribution of peatlands. So if the biome were to shift northwards, this may become, you know, the climate may become less suitable. And there is another compilation that was also done using paleo data, using these beautiful tested amoeba proxies that we can use, looking to see if European peatlands are getting wetter or drier. And the finding was that generally there is a recent drying of European peatlands. And this is, I don't think that, yeah. So this is all sites, Britain and Ireland, continental Europe and Scandinavia and the Baltics. But there is drying in all of those systems. And it's probably a combination of anthropogenic impacts together with climate change. But, you know, the worry is they're really drying quite a lot. You know, is that pushing them out of their sort of functioning thresholds, you know? And that sort of fits, for example, with a modeling study that is also actually somewhat based or calibrated on paleo records, but, you know, using a bioclimatic envelope modeling approach. And I just thought, since we're in Scotland, I'll show you this, is blanket bogs. And, you know, is how that envelope, blanket bogs are very dependent on climate. They're very dependent on precipitation. You know, if the envelope changes, if that climate changes, how they might, you know, change. And so this shows kind of disappearance, not of the peatland itself, but of the climatic envelope that allows that peatland to function well. So it doesn't mean that the peatland will disappear. There's resilience in the system, but it means we're probably pushing it to a state that is not as functional, let's say, as it is now. And then in tropical peatlands, I didn't know what to say about tropical peatlands because we know very little about tropical peatlands. We know very little about tropical extent even. There is some mapping efforts. I think that I put here, stay tuned for the GMC Global Peatland Map Release on Tuesday. But basically, we don't understand very well what controls the exact extent of tropical peatlands in the present time. And so it's very hard to say how that might change in the future. But likely hydrology is key. So if hydrological changes that we know are happening in the tropics, you know, we hear about drought affecting the big forests in the tropics, those droughts are gonna also affect our peatlands, right? And I just wanted to put this here because we know very little about tropical peatlands, but what we do know is that this is, you know, from a relatively recent paper. I'm sure you've seen this in other talks, you know, suggesting that actually tropical peatlands are pushing that, you know, are pushing our, well, it suggests that from the 1960 global peatlands already became a sink, and that release of carbon to the atmosphere is likely to increase if we do nothing because of anthropogenic pressures on tropical peatlands. So what I mean is, all that I'm saying is a little bit, well, not as important as the land use changes that we're already seeing in the tropics. So the takeaway messages from this part is that it's likely that the peatland biome might shift northwards, but watch this space because the projects that we have might give us some answers. Hopefully there is some resilience built in the system, and it will be very dependent on changes in hydrology, which we are less certain about. There may be that some peatlands at the edges of distribution, like temperate peatlands, might be suffering more, and tropical peatlands, we need to know more, and before they're destroyed. And then I'll pass over to Julie again.
Thank you. Right, I will take you back to Alaska for a little case study here. And we've been hearing about these northern peatlands increasing their carbon sink capacity because of a longer growing season that increases photosynthesis. But here I want to show you a different example of what might happen to promote that carbon sequestration. And it also addresses something that I spoke about earlier, the fact that in the peat record, we see the very recent past, we have these really rapid accumulations of carbon in the cores, but we really can't tell, is this climate change that's positively impacting carbon sequestration, or is this just because this peat is not decomposed? And so we're trying to tackle these problems a little bit using the Paleo approach. So here what you see is a real core from Alaska, from that site that I'm describing, and we had multiple of them across the landscape. And we did multiple proxy analysis, and here you're just looking at different plant fossils in the core, and we also look at pollen and those little amoebas to reconstruct changes in water table depth. And essentially what we see is that there's a big change here between this very mucky, yucky, decomposed peat to this very beautiful, fresh-looking sphagnum peat. And we were wondering again, what is this? Has it always been a sphagnum site, but it's just re-decomposed, and now recently it's that stuff, or is this a new shift in the ecosystem? And the Paleo allows us to answer that question. And there was no sphagnum all the way up until about less than 100 years ago that we were able to date using multiple methods. And there's no pollen or spores in this case of sphagnum either. And so we are thinking that sphagnum is a new phenomenon in some of these peatlands. So you can imagine a landscape in Alaska that used to be kind of crappy, unhappy peatland. It's wet and there's like these grasses growing and the carbon sequestration is just very slow. And now the climate is warming just enough that the water table depth is decreasing and sphagnum can invade and colonize and spread very rapidly. And since this sphagnum doesn't decompose as fast as these other types of plants, they're really capable of putting on more carbon. Okay, so that's the working hypothesis. And we see this at multiple sites. Now, what we did from a modeling perspective to try and quantify this change and how it would impact the carbon sequestration is we look at the top, which we call the acrotelm, so that recent peat, and we look at the bottom part, the catatelm, which is that old, like, mucky-looking peat. And we back calculate using the real cores how much production was happening many thousands of years ago, and then we can take the top of the core and we can forward model how much decomposition will happen in the next 200-300 years before it becomes old peat. And then we can compare the two numbers. And what we found, and I don't have all the equations here, but I wanted to keep it simple, but what we found is that there's a 4 to 10 time fold increase in carbon sequestration since that new change in ecosystem, even if we back calculate the amounts of net carbon input from a long time ago. And so just to put this into context, what we think is happening is that warming is drying the surface, again, just enough. It's like this sweet spot for the peatland. And so sphagnum is accumulating and is creating this rapid vertical growth. And that peat formation enhances carbon sequestration. And of course, that feeds this negative feedback loop that slows down climate. Of course, it's not happening like enough to slow down climate change, but it's still going in that right direction of putting carbon away. So that was just a brief example, again, of how we use Paleo to understand the present and the future. And then we will talk a little bit about what our group is going after. And so, first of all, peatlands are not quite integrated into Earth system models. The thing is, the paleo record should be really considered an important piece of information because it provides all these things. First of all, a process understanding of how peatland develops over time, data to calibrate and evaluate multiple types of models, these empirical bounds or reality check on models, because models can tell you whatever you want depending on kind of information you put in there. And so we need to really test against real peat cores, and then the natural range of variability that happens in natural system, and also the rate of change that has taken place through time. And of course, we know that droughts, floods, fires, permafrost thaw, permafrost growth, all those things have happened in the past. So we have a record of it that we can really exploit and try to understand how those systems work. But peatlands are starting to be integrated actually in ESMs, and I'll let Angela talk about it.
So we just wanted to say that the community has been also working with modelers to help them calibrate and evaluate their models. So an example of this is Orchidée in the French land surface model that has recently incorporated northern peatlands. So a lot of the models now are trying to incorporate at least northern peatlands. But they don't incorporate fully all of the processes that we think are important, like hydrological feedbacks, for example. But they're already starting to simulate the future of northern peatlands. And you can see an example here. This is a change in carbon stocks in northern peatlands in the future. And you can see red means an increase in carbon stocks in northern hemisphere peatlands. So they are sort of, but there is no agreement. So I will show you now another land surface model. This is the Bern Lpx model, and it basically suggests some increases and some decreases of carbon accumulation in northern peatlands. So they don't really agree, but there is also led by the same group, led actually by the French group, but including all of the land surface models that are not very many that have peatlands in their, so land surface models are all of the dynamic vegetation models that exist that have a northern peatland component. And here, this is actually in press, but it will hopefully soon be published. But it's a first appreciation of the uncertainty when you get all of the models together, what will happen to the carbon. So here is, for example, that gray or green, what is it, green? I'm blind. Greenish yellow line, and the uncertainty is for RCP 85, the model range and ensemble mean. And you can see that for all northern peatlands, it starts increasing, but eventually it decreases quite rapidly. While for RCP 2.6, there is not such loss of carbon, let's say. This is for the model mean, but you can see that the uncertainties are quite large. And then it's divided here in these panels for each of the regions in the globe. And again, they've used the compilations that our group has done to calibrate these models.
Well, like Angela was saying, we have these land surface models that are starting to integrate peatlands. However, they really are using a simplistic, I don't want to use simplistic, simple representation of peatland dynamics and vegetation. And so we took a slightly different approach, the expert opinion approach, to try and put numbers on the future carbon sink capacity of peatlands. And here we had a bunch of peatland scientists work together to identify what are the main agents of change that are impacting carbon sequestration. And you have them here on this, this beautiful drawing, actually, that comes from the same artist that did the paintings around here. So we have temperature, moisture, permafrost, land use change, atmospheric pollution, sea level rise, and fire. And what we did is we asked everybody who wanted to answer the survey and who qualified as a peatland expert, what is the role of each one of these agents of change in the past, the present, the near future, and the far future? And then we started trying to put numbers on this and trying to see if there's consensus or not. But before I show you the results, I just want to talk for 1 minute about the expert opinion approach, because at first we were thinking, we're scientists, we don't want to just asked people for their feelings, you know? And so I just want to reassure everybody, this is not about feelings. Everybody who participated had to explain with citations and numbers where their numbers come from. And also don't forget that a model simulation, in fact, is everybody's knowledge put together and put into equations. But as scientists, we've been in so many peatlands, we think about peatlands, and we integrate all this knowledge like a little bit like a mental map, and we can have our own model in our mind. And so this is where it's based, and a mix with the synthesis of the literature. Okay, so with all that said, we feel more comfortable, but still anyways, I'll get going. Okay, so here are the results, and the top panel is the past, so what we know from real studies that we've done on peat cores. And you see in blue are the northern hemisphere peatlands, or the high latitude, and the yellows are the tropical sites. And temperature, moisture, sea level, all of those on the right-hand side means that those agents of change are sequestering carbon into the peatlands, and everything on the left shows carbon sources to the atmosphere. So fire, land use change is what is negatively impacting peatlands. So we're not surprised about the results, which is good. We're understanding the systems correctly. And then what became interesting is thinking about the future. So how do we apply this knowledge and try to project what would happen? And the really big picture answer is, look at this. In the Anthropocene, which is the recent past, we still see lots of carbon inputs into the ground. But as you look down into the future, the more and more bars are on the left side, meaning release into the atmosphere. And so we compiled all of this to actually sum it all up. And we estimate that between 2021 and 2100, there's about 100 gigatons of carbon that could be released from peatlands. But the error bars are gigantic because this is an expert assessment again, so we really want to stress that. And also what is even more important to me is to show the individual responses from all the experts. So each dot is an individual answer on those sheets of paper from the, I'm writing, but it took a long time. They were actually using computers. Yeah. And what you can see is that for some of those agents of change, there's dots on both sides of the line. So we don't even agree as a community. You know, for example, is permafrost going to release carbon to the atmosphere or sequester carbon to the atmosphere? Because some of us, we have our biases depending on where we work. And so at some sites, when the permafrost is thawing, there's water that is ponding, of course, but then there's really rapid growth of plants. And so that could maybe store some carbon, whereas other sides, the water goes away very rapidly, and then you can have massive CO2 release. And so there's all these different processes that people are kind of internalizing and trying to quantify here. And long story short, that's why we have kind of these lacks of consensus, which we find really important because it's really showing us where we need to do more research and understand the processes better. And I'm just putting all the definitions here because this will be online so people can look at it later. And so, yeah, essentially, the big question about whether or not the peatlands will become net sinks or sources is an unresolved one, and one that we don't really have a consensus about. But there is one thing, is that when we lose a lot of carbon, like I was telling you, 100 gigatons by 2100, it's really related to land use change in the tropics. This is the one thing that people were really agreeing on. Yeah. And the good news about that is, well, it's humans' fault, so we can also stop it if we choose to. And about that, something that we love to think about, and we're hoping to start building bridges with people who are doing restoration and also finance of peatland conservation, is all of these massive, pristine peatlands that are on the landscape, not the ones that are destroyed and that need restoration, but the ones that are still untouched. What do we do with this? How do we prevent further degradation of them? And I think the economist yesterday or a couple of days ago, Ed Barbier, was saying it's so important to restore sites, but also we need to not touch the ones that are good. So we want to present this idea, very simple, of carbon parks. And essentially, we've heard a lot about natural climate solutions. And the Paleo approach can help us identify where we want to prioritize conservation, perhaps, and even restoration, and discuss or think about climate resilience to those restored sites. But maybe that's for a different discussion. But in terms of carbon parks, what we're trying to show is that restoration provides this financial additionality that is very attractive for corporations. But in the case of a peatland that's functioning normally, there's really like no money to be made because it's just doing its thing. So how do you incentivize people to protect them? It's difficult because the peatland is just doing its thing for thousands of years, and we just want to leave it alone. And I'll leave this up later because there's a lot of text here, but essentially the idea is that if we could have a designation of carbon parks that is not a protected area, it could be just a way for people to really recognize the importance of carbon sinks, a little bit like the dark sky designation that exists around the world that limits, say, building a skyscraper. You wouldn't do that in a place that is designated for a dark sky because people would look at you like, what are you thinking? You know, we're trying to keep the sky dark. So if people got to know more about peatlands and their role in the carbon cycle, it would really disincentivize, hopefully, people from going and building. And so the carbon park idea is really just to recognize the natural carbon stores. And it would work for peat, but it could work for grasslands, for forests, for other types of ecosystems that are rich in carbon as well. And I know they want me to stop talking. And rather than a financial additionality, we were thinking if there was a way that we could put money on the climate stabilization service of those ecosystems, that could be potentially a policy instrument that could be utilized also to help finance the carbon parks. And the carbon parks could be more like a grassroots organization. So anybody who would want a carbon park to be recognized could utilize it as an educational hub, for example, to really talk about the importance of those kinds of ecosystems. Because in my classroom, when I start talking about soils and carbon sequestration naturally happening in ecosystems, my students are looking at me like they don't know what I'm talking about. And they're in environmental science programs. So I believe that a lot of people are probably in that same boat. So something along those lines that would be very simple, and just the title in itself should tell them, oh, what is going on here? Perhaps could help this communication with people who are non-scientists. Yeah, so that's the idea. And we would love to talk more about whoever is interested in this. So with that.
The last slide.
Yeah, the last slide.
This is our general conclusions. So we just wanted to say that our community is working hard to understand paleo peat records and to inform our managing of peatlands really and our future predictions of peatlands. We have done a lot of large-scale carbon synthesis work that we think that has shed some light on how peatlands function or have functioned in the past. We also used, not only the large-scale reconstructions, but also local-scale reconstructions are helpful, especially if you're managing a peatland. For example, like Julie was saying, if you're restoring a peatland, what is your aim? What's the aim that you're going towards? Paleo can shed light on that, for example. That we think that, well, we are actually involved in now proxy data synthesis, and we hope that that will be useful for modeling so that we can learn something about the future. And this idea of carbon parks that Julie has just put very beautifully across. And I think that's it. We'll take any questions from the audience. I was gonna say, or from the online, I don't know, from the online audience, or we'll take also questions by email if the online audience would like to email us.
Yeah. Otherwise, we'll be here.
And I didn't realize that was Peatland.
Can't hear. Did you hear it?
Oh,
Oh yes, they're great, great.
Sorry.
Microphone,
You'll have
great.
to start again, sorry.
Just what constitutes a peatland? What are the basic attributes that it qualifies it? And then the effect of wildfires in terms of restoration if there is wildfire. And then a question just about the red list of ecosystems if peatlands are sort of on the criteria list. Thanks. Excellent presentation.
Thank you.
Ooh, excellent questions.
Excellent questions. Shall I start with the first one? What is a peatland? Sorry, we didn't actually, we had a slide saying what a peatland was, and then we removed it because we were in the peatland pavilion. We thought it was too basic. I think I'm going to take Gustav's definition. So a peatland is an ecosystem that has more than 40 centimeter of organic matter or peat in the soil. It's just a definition. Well, it differs by country actually, and that creates problems. But it's normally, like a peatland is a wetland, so it's normally a wet ecosystem, unless the water is frozen, in which case it may be dry, but it's a wetland, and it's a wetland that contains organic matter. And then the definition, you know, how deep is that organic matter layer changes by country, which causes loads of problems in terms of mapping, accounting of carbon stores, and so on. That's the first question. The second question was...
Yeah. Oh, yeah.
Julie?
You know, and we should have said we have a compilation that is
Oh yes, we forgot to
ongoing,
say.
looking at the past 10,000 years around the world and looking at charcoal, because we can see charcoal layers in the peat record. So we're trying to understand fire, sensitivity of peatlands to fire and all of that. Fire, that's such a loaded question. There's, let's see, in the tropics, there used to be very little fires, for example, in the peatlands, and based again on the paleo record. But today, because of the compounding effect of land use change and degradation of the sites, combined with, for example, droughts during El Nino years, the fires, when they come in, they burn down not only the trees, like you're used to thinking about, like a forest fire, but they can burn also significant amounts of soil that dries out. And I think sometimes it's equivalent to almost an entire year worth of human emissions. So we're starting to hear about it in the news. In Indonesia, a few years ago, there were giant fires in Alaska, a few years ago as well, and then in Russia.
Yeah. So they're happening more and more. I mean, even here in England, we have had wildfires on peatlands now. So fires are becoming a more common phenomenon, even on wetland ecosystems, where really normally there would have been some fires, but not very many. You know, only in extreme years, I guess, but those extremes are becoming more common. So it's becoming a problem, and definitely, you know, a fast release of this old carbon into the atmosphere.
Yeah. And oftentimes, since we have a record, it means that the peatland does come back. But you know, on the time scale that is relevant for policy, it makes it very difficult, because if it takes decades, for example, sometimes it takes less than a decade for the peatland to start again, but you still might lose quite a bit of years of carbon accumulation. But we're not fire experts, so that is all I will say about this. Yeah, and in terms of peatlands on the red list, I want to say that some of the PASA peatlands might be ecosystems that are threatened, quote unquote. And so there's some types of ecosystems that are fairly rare, including the blanket bogs, but also in the permafrost area, there's some PASA, and it's a very special and fairly rare type of ecosystem. And they are also unique for biodiversity and other aspects. And so they are on those lists. But in general, peatlands, I don't think are part of those lists.
Gustav, do you know? No, I don't know.
I think PASA is, yeah. Yeah, thank you for your questions.
Thank you.
Yeah.
Yes, with the mask, we can't hear.
It's so difficult. We can't even read on your lips.
How do can you hear me now? Okay.
Yeah. Oh, we can't hear.
Oh, we need, thank you.
How do peatland regenerate? You know, you said you can see in the paleo history that there were some fires and then they regenerated. And what are the factors for the peatlands to regenerate?
It's a good question. I can hear myself. It's a good question. So for me, I do large synthesis, you know, modeling, and I think whenever the climate or the conditions are right, you will have regeneration of peatlands. So if it's wet enough, let's say, if the climatic and topographic, I say topographic because sometimes you don't need to have a lot of rain, but just a bowl where the peatland can develop. So whenever the conditions are right, you may have regeneration of peatlands. In fact, for example, in the UK, there is some self-regeneration of really naked peatlands in those areas where the conditions are right. So sometimes regeneration can happen because of compaction of the peatland column that makes the water basically is held more and the water table rises, and then that's enough to regenerate. So wherever you have the right conditions, you may have regeneration. When the peatland has been drained, you need to block those drains to make the water table rise in order for it to regenerate. And in some instances, you may need to help, with input of the right vegetation. But in general, the system should it should start again if the conditions are right and there is sufficient, let's say, genetic material around the site to bring the flora back.
Exactly, and let me just add very briefly an example of that, because the peatland surface, and I'm sure you've walked on peatlands before, it's not like this flat area with a single type of vegetation. So they tend to have these little hummocks and hollows with different types of vegetation. And for example, in the boreal forest, if you have a fire that goes through, oftentimes it's because, let's say it's dry, the surface is dry, the little depressions are completely dry, but those hummocks are made out of sphagnum, and sphagnum, they grow like this, really tight, and so they hold on to the water. So even if the fire goes through, those hummocks don't burn. And so you have a really crazy looking landscape of everything burned except these hummocks of sphagnum. And so the peatland can regenerate or restart pretty quickly. And so there's these kinds of resilience built in the system. So that's why they can survive. I think, yes.
One here, and we've also done one online.
Oh, okay.
Thank you so much. It's really interesting. Can you hear me? Hi. Thank you so much for your really interesting presentations. I wanted to ask about grazing and management of the landscape, because in the UK there's sort of excitement around rewilding, and then there's sort of the whole like farming issues, and I know that there's quite a lot of sheep grazing on upland areas. So I wanted to know if that is bad for peatland or good, or and how you see that under climate change and management going forward. Thanks.
Ooh. Do you want me to answer?
That's a hard question. You go ahead, since you're from the UK. Or you live here.
So if I talk to you as a scientist looking at the carbon cycle, if an animal is eating away the carbon, you remember that I was talking about carbon accumulation being the balance between the carbon that the plants uptake and the carbon, the decomposition of that carbon. By grazing, you're decreasing that amount of carbon that comes into the system. So you're basically overall decreasing the carbon accumulation probably. But there are other issues with it. So you can have, a small amount of grazing that wouldn't make a big difference, but overgrazing that might make a big impact on the system. Also from compaction of the peat itself. And also many times, if you want a peatland to be grazed, you need to drain it in order for the animal not to sink into the hollows and so on. So the problem is not just the grazing, but is the management, the lowering of that water table that will release that carbon into the atmosphere. So what's the solution is very difficult. I mean, I'm not going to say that, there should be no grazing at all on the uplands in the UK. I'll probably be, yeah, I don't think I want to say that in public, but it's one of those difficult decisions. There is competition for the land in terms of how we use it, and we need to decide what's more important. Feeding people obviously is essential, so we need to feed the population. So I think that is one of those tough choices that we need to make, and it does have an impact on the system, especially if you drain it. I can't say that it doesn't have, but there is also the other side of the coin that these land uses have been there for a long time. They're part of the culture and so on, and it's tough decisions, I think.
And that's the similar problem around the world when the peatlands are being utilized by communities, and it's their livelihood that we're talking about. And I think there's some compromises that people are trying to make, and we were talking with somebody from the République démocratique du Congo a few days ago, and he was giving the example of small farmholds on peat, and he said, well, it's releasing some carbon, but it's that or large-scale farming, and you choose the lesser of two evils in a way. And perhaps there's something like this to be said. So there's maybe a more sustainable way to do some grazing, but
Yeah.
you can't just say no.
And I would say, you know, in terms of ecosystems on Earth and where should we be grazing our animals, peatlands are really, really effective carbon stores, effective in the sense that they are very carbon dense. So, you know, they occupy a small space, but in exchange, you know, they have a lot of carbon volume. So I think that maybe we need to take a global approach in terms of thinking about where we grow our food, where we graze our animals, and so on, you know. I don't know if that answered the question.
Thank you for a really nice presentation. You know, you give a very nice overview of, you know, all the different work and all the different things. So I'm going to zoom in on a slightly more scientific question. You were telling us about the two components to peatland growth. You have the vertical growth and you have the lateral expansion. And you were also telling us, you know, how incoming solar radiation really seems to control growth. Do you think this is true both for lateral and vertical growth, or do you think that the lateral growth could have other mechanisms behind it?
Absolutely. Yes. So I think the vertical growth is more controlled by temperature, radiation, and the lateral is more controlled by moisture. So I believe that moisture is the controller of the expansion shrinkage. The only thing is that, you know, they're not always completely separate. So, you know, sometimes if you have warming, then you have drying as well because of the increased evaporation and so on. So they're not completely separate. But I think that moisture is really the key factor on expansion shrinkage.
I agree. I have no further comments. Okay. Thank you. Do you know a communication plan to present your idea of carbon parks to petrol or mining industry developing in the north? So to go to different type of conferences.
And let you ask that question. So I'll read the question aloud so that the people here can know what it is. Do you have a communication plan to present your idea of carbon parks to petrol or mining industry developing in the north? So to go to a different type of conference?
That's a good idea. We do not have a communication plan specifically for those kinds of stakeholders. I think right now we want to see if carbon parks would be a concept that people would be interested in. First off, how it would really look like. If I say carbon parks, what do you see? And we have some ideas, but we would like to really think about this more
So
with
we thought
others.
this was a good place to start?
Yes. But I see where that person is going in terms of especially protecting the north, where this is where a lot of those carbon parks could be located. The idea is not so much to make the pitch to the mining industry. It's more that the more people, the general public, recognizes the importance of the carbon stores, it just becomes a nonsense to destroy them. It's just like, we want it to be obvious. As soon as you say peatland, we want people to know what it is, to know that they contain carbon and that they should be, untouched if they're still pristine. This is like 5 steps down the line from where we are at this point, but it's a good way to think about it.
And also just to say, I know that we are very focused on carbon. Our group is C-PEAT,
yes,
but we absolutely recognize all of the other benefits that peatlands have.
Yeah, can you name 1 or 2? No, I'm kidding. Water. No, I'm just joking.
Yes, thank you for your very. Oh, sorry. Thank you for your very interesting and concise, comprehensive story. I only pick out one issue to discuss further on what we have been hearing just about the carbon parks. It is also a criteria under the Ramsar Convention. They have introduced a new criteria to designate Ramsar sites for climate change mitigation. And we are actually in the situation that the Paris Agreement actually prescribes or implies that we have to keep all the stocks there. And we made, for the Ramsar Convention, a rapid calculation where we are talking about. In the end, you have to protect all the peatlands. That is very clear. And where you are talking about, for example, if you protect all the polygon miles in the Arctic, we talk about 1% of the carbon in the peatlands. And when we protect all the peatlands of Kalimantan and Sumatra, we are talking about 5% of the world carbon in the peatlands. When we protect all the peatlands of Western Siberia, we only talk about 10% of the carbon in the peatlands. So, of course, carbon parks are a very important instrument to mobilize the thinking about that. But in the end, everything has to become a park. That is clear.
Yeah, absolutely.
Yes. Thank you for those calculations. This is really interesting. And like we said, first of all, it would not only be for peatlands, and yeah, maybe to your point, everything should be a park. And yeah, how can I answer this? I think what really matters is the message, and we don't want to make parks protected areas. Like Ramsar has these designated areas, and that is one thing. And absolutely, some of the carbon parks could also be protected areas or Ramsar sites that are recognized carbon sinks and education hubs. But it could also be a green roof in a city where a lot of people can go and just understand what what an ecosystem storing carbon looks like. And I know I'm circumventing your question a little bit, but I think it's really the idea more than the actual amount.
Yeah, we have a colleague, Dylan. He has a little grassland in his backyard, and he was saying he wanted to ask his neighbors not to mow it 1 year, and the neighbors were horrified. And the idea, I think, with the carbon parks is maybe to make
garden park.
Is to make peatlands more, I don't know, more easy to understand why they're important in a really simplified way, let's say, so that his neighbors, maybe if it was a peatland, wouldn't be horrified that you say, you have a carbon park in your backyard.
Yeah, that's also some of the criteria that we formulated for the Ramsar Convention. Of course, when you talk about really the climate effect, you talk about protecting everything. That is clear. But you use carbon parks as a communication instrument, and then you have to select them that they are maximally communicatable.
Yes.
So that they are, for example, close to population concentrations, that they show the problem. The first peatland that was designated under this criteria was Lille Wildmoser in Denmark. And that is an area where you see a still pristine peatland next to a drained peatland, where you can easily communicate the problem. And so it are communicating instruments that you have to select on this property.
Yeah, and we want the selection to come not necessarily from the experts, but from local people who have either an important connection to the land. It could be that, or it could be in the example you said, or perhaps somebody who has a nice ecosystem in their backyard that they want to. So it can be very small, but we want it to be bottom up rather than top down. So we want to not redo what, say, protected areas have been doing in the past, and really work with people from the areas.
I just want to say I'm really touched that you've all stayed this late. Like, we were expecting only Gustav to be in the audience. So we are very grateful to you for all these interesting questions.
This is great.
Oh, one more question.
Oh, that's good. Thank you.
Thank you very much for your presentation. So if I understood well, there's still some uncertainty whether climate change is going to turn peatlands into sources or sinks of carbon. And because we're at COP today, and because there are negotiators on the other side of this wall, I would like to know from each of you, if you had the opportunity to talk with these people, what would you tell them? What would be your recommendation to the negotiators?
Okay. If I had to say a very short thing to them, I would say that if they forget peatlands, they will never reach net zero. So peatlands must be on the table and must be considered. I think that's the message. I mean, they've been really neglected up to now. We thought that they were inert in terms of carbon, and now suddenly we see that they're big emitters. So we know they're not inert. We know that we can really release all this carbon into the atmosphere. We just cannot ignore them. This would be my message.
And I would add on this, and I would tell them in the northern high latitudes, climate change is getting to them. In the tropics, land use is getting to them, and it's compounding with climate change. And so no matter what country you look at, peatlands are changing right now. So we really need to consider them. Yeah,
But I don't think they're listening.
I think they're having a beer.
A beer, yeah.
I think FAO
You can just speak up.
has formulated very nicely already in 2012 in the framework of the discussions on the climate convention. Protect wet peatlands, restore degraded peatlands, and if you need to use them wet.
Yes,
That's are the three basic rules.
I like it.
Perfect.
That's even better. He's
That-
hired.
He can go and talk to the negotiators.
Yeah. Just go back into our labs. Well, thank you again.
Fantastic presentation. Thank you very much.
Thank you.
Okay.